But then there is genetics, which shows that we share about 90% of the common genes
97% of our DNA.
90% genes, sorry?
with apes.
No, it doesn't.
How much?
Well,
Let's say 90. I went on a limb, but let's say 85.
no. What it basically is that when you're doing a genetic comparison between two organisms,
Yep.
you have to make some assumptions if you're going to say there's a percentage difference between the two. So if I was to ask you, in terms of the human-chimp genome, how much percentage of the human-chimp genome is similar in terms of orphan genes, right? Orphan genes are particular types of genes. Do you know what that percentage is?
Can you explain again?
Okay, you said 90% of the human ape genome was similar.
Yeah.
Now the thing is, whenever you do a comparison between two different genomes, you have to make some assumptions there. There's no such thing as an objective analysis like two books. Like I got one book and I got another book and then I say
80% of the words there.
80%, yeah, you can't actually do that because there's a few assumptions you have to actually make. Now one of the things is, what most people don't know is that the way that they calculate the percentage differences is they look at what's known as biomacromolecules. So they look at DNA or RNA or proteins.
Yes.
Now, depending on what you select and what you leave out, you can come up with different percentages.
So what is your percentage?
Well, I'll give you some percentages, right? If you look at the percentage difference in terms of orphan genes, if you're to look at orphan genes,
Like O-R-F?
orphan, O-R-P-H-A-N.
Okay, like orphan kid?
Orphan kid, yeah.
Okay, we got orphan genes.
So you got orphan genes. I hope I spelled it right.
And what is it, orphan genes?
Orphan genes are particular types of genes which we have in organisms, right? Now you have an orphan gene in a human being, and you have orphan genes in the great apes. And if you were to do a comparison between the orphan genes, you'd actually come up with 0% homology. 0% difference. But if you were to look at the proteins, you'd come up with 20%. And if you were to look at, say, certain molecules and ignore the rest and say that, okay, do you know what we're going to do is we're going to look at what's similar and we're going to ignore what's different, then you can come up with 99%. But it's very subjective because you're picking and choosing, and according to that, you can come up with whatever percentage. But I'm assuming you believe in human chimpanzee history.
Well, no, okay, let's go back continuing on what you said.
Sure.
Okay, let's say my number is not correct. Let's say the methodology is not exactly accurate, and
I'm not saying it's not accurate. I'm saying it's based on assumptions. There's a difference.
So let's say the commonalities is more like 30%.
Okay, no.
Let's go on a limb.
Okay. Let's do this. Let's say the commonality is 100%. Okay, commonality is 100%.
But it cannot be square different.
Okay, say it's 99.999%.
Okay.
Let's assume that. The fundamental assumption here is that similar genomes means a common ancestor. That's the assumption.
Yeah.
Right?
Yeah.
Now, here are some of the reasons why this assumption is not correct.
Okay, please explain.
We have PAX6 genes, which are for eye development. We have them in fruit flies and we have them in human beings.
Yes.
Yet those are not due to common ancestry. We also have genes for echolocation in bats and genes for echolocation in dolphins, which both code for echolocation, but they're not due to common ancestry. They're known as what? They're not known as homology. They're known as homoplasy. So one of the issues that we have in biology is that we have identical things which exist within the tree of life, which are identical in terms of their genes, which do not have a common ancestor. So the fundamental assumption that similarities equals common ancestry, that assumption is challenged by homoplasy. So I'm not saying it's not accurate, I'm just saying it's based on an assumption.